Hi, everyone. Thanks for coming today. My name's Eric Jansen. I'm an analyst with the Toronto and Region Conservation Authority, and today I'm going to be talking about thermal mitigation of stormwater management pond outflows using geothermal cooling. First, a bit of an intro to me and to my organization. I'm from the Sustainable Technologies Evaluation Program. It's a collaborative initiative between the TRCA, Toronto Region Conservation Authority, and other conservation authorities as well. There's two components to STEP. There's STEP Energy that evaluates energy efficiency technologies for buildings. And then there's STEP Water that evaluates technologies that protect water resources. And examples of that would be erosion and sediment control, thermal mitigation, salt management, LID, and things of that nature. So there's this broad umbrella as STEP and these two groups operating underneath it that more or less do different things. My educational background is in physics. I have an undergraduate in physics and then a master's of applied science in engineering physics, looking at solar energy specifically. And I've been an analyst with STEP Energy since 2013 and spent a little bit of time in industry before that as well. Now, my role with STEP Energy is as a scientific lead on the different pilot projects that we do related to renewable energy and heat pumps specifically, and geothermal would be included in that category. My colleagues over at STEP Water have done a lot of work in this area of thermal mitigation, and they brought me on board to lead this project using geothermal, essentially taking an energy technology and applying it to a water problem. I think it's an interesting example how you can get some maybe out of the box thinking and some innovation that happens when you have interdisciplinary problem solving. And also, just as the disclaimer for my talk today, that I was brought on as the geothermal expert in this. And my knowledge in thermal mitigation generally is not up to the same level as some of my more knowledgeable colleagues. So I'll do my best to provide the adequate context and discuss any questions, but I may need to defer if they're on thermal mitigation more generally. Here's an outline for the talk today. The issue that I'm talking about is thermal pollution. The solution to that issue that we're proposing is geothermal cooling. We're going to talk about some modeling. After all, this is a modeling conference. And then also some results from a recent data monitoring pilot that we did that was funded by the city of Brampton in Ontario, Canada. So the issue that we're dealing with is that if you take a natural landscape and cover it with a hard impervious surface like concrete, you have to do something to manage the stormwater pond and the stormwater. And a popular way of doing that is a stormwater management pond, and these are really common throughout the GTA. An image is shown in the bottom right there of all the different stormwater management ponds. So this solution works, but it introduces a new problem. The surfaces like concrete and other urban surfaces heat up in the sun, and the rainwater that hits them is pre-warmed before it enters the pond. Then that water sits in the pond for a long period of time, potentially, and it's a relatively shallow pond. The water heats up, and then it's up to 10 degrees warmer by the time it reaches the stream than it otherwise would have been if it was just a natural landscape. So this is a problem for aquatic life that are sensitive to small changes in temperatures. Example would be cool or cold water fisheries. And there's been some recent regulations and acts that have identified maximum targets for these ponds, and also identified that retrofitting some of the existing ponds is an important action to benefit some of the species that are at risk, like the endangered red-side dace. Now, of course, there's many potential solutions to this issue. I'm not going to discuss them all today. My colleagues over at STEP Water have done a comprehensive data synthesis looking at the performance of all these different techniques. What we're going to focus on today is just cooling trenches because it's a very popular method. So what is a cooling trench? It's essentially just a dug trench that's downstream of the pond outlet. It's filled with clear stone, and the idea is that water flows through this on the way to the receiving stream. And the thermal mass of the stone and the heat transfer with the surrounding ground provides some sort of passive cooling. Now, my colleagues at STEP Water have done some monitoring of these systems and reviewed the data that was available for other systems as well. And they found that more than half of them are actually not working that well at all. We're not going to get into the details of why that is, but it's important to acknowledge that there's many factors that influence the performance of these systems. However, what they tell me is that in general, if we want a passive standalone cooling trench to work and meet our targets, it really needs to be quite large, and that can be difficult to achieve in practice. So this data synthesis is available on our webpage. Full report and a short white paper is available as well. I think the important takeaways for this discussion is that this issue of thermal mitigation for new ponds isn't solved. We don't know the best way to do it yet. And we also need a solution for retrofits of existing systems that are underperforming, and there's actually many of these. Okay, so that enters, let's enter into geothermal now. So geothermal is something you're probably familiar with. It uses it as an energy efficient heating and cooling system for a building. It essentially uses the stable temperatures of the deep ground as both a source and a sink for heat energy, depending on whether you want to heat or cool a building. The heat exchange interface with the ground is accomplished by one or more deep vertical boreholes. In the bottom left there, I'm showing a cross section of what that looks like. Essentially, you have a drilling rig. It bores a hole maybe about 5 inches diameter deep into the bedrock. Common depth for large buildings in the area of Toronto is 600 feet. Inside of that borehole, a U-bend of plastic pipe is placed, and then the whole thing is backfilled with a thermally conductive grout. So what happens is there's a heat transfer fluid. It goes down one side of that pipe in the borehole, goes all the way down, and then comes back up again. And you get heat transfer between that fluid and the ground, depending on the temperature difference. Now, if you combine this with a heat pump, you get a really energy efficient heating and cooling system for a building. What's also possible is pond-based systems. We have one of these in downtown Toronto that does a lot of the cooling for the downtown core. Same basic concept. We have a network of piping. In this case, it's sunk to the bottom of a pond. A heat transfer fluid flows through this network of piping, and then you get heat exchange with the pond, either heating or cooling the fluid, depending on the temperature difference. The insights that my colleagues over at Step Water had was, what if we connected a deep vertical borehole to something like a pond-based geothermal system to cool a pond? We're not talking about cooling the whole pond, just the outflows, but you could see how we could use these deep ground temperatures potentially to cool the outflows that are coming from the pond. This is an overview of the system. It's really just a large closed loop of piping. There's a fluid that's circulating around it. It's a non-toxic glycol solution that can allow the system to be freeze protected. So there is a circulator pipe, a circulator pump that's causing the flow. In terms of the other components, we have a surface water heat exchanger. It's placed in the path of the pond outflow. We have a ground heat exchanger that's composed of one or more deep vertical boreholes. And then we have this fluid flowing around. So let's just have a look at that. The fluid is represented as the blue circle here. We have a relatively cool fluid being supplied by the ground heat exchanger. It's absorbing the heat energy from the warm stormwater, cooling the water and heating up the heat transfer fluid in the pipe. That's being pumped back to the ground heat exchanger. Water goes all the way down those, or the heat transfer fluid goes all the way down those boreholes and all the way up again, and the fluid is heat transfer fluid's cooled back to its original temperature again. So in this way, we're absorbing heat energy from the water from the pond and rejecting it to the cooler deep ground. And again, we're only cooling the pond outflows and not the whole pond. Now, the good news is that because these systems are from an established sector already in heating and cooling buildings, the math is already quite well defined. So it's a physics-based analytical steady state heat transfer model that in our case we would solve numerically, but that's quite easy to do. What we had to do in our research was essentially take the math for the ground heat exchanger and the surface water heat exchanger and just put it together to create an overall system model. This table shows all the parameters that are important that govern the system performance. If we're going to do a design procedure, we would take for example, a set point temperature that we want to meet. Let's call it TP2, might be 24 Celsius. We would know the temperatures coming from the pond and the pond flow rates as well. Then we can estimate or measure some of the other parameters. For example, the thermal resistance of the ground heat exchanger and the surface water heat exchanger. These are just numbers that we would know from other geothermal installations. We'd estimate a deep ground temperature as well, TG. And then we could do a cost optimization calculation to size the lowest cost number of boreholes and also length of piping required to achieve our set point temperature. So the good news is that this is all well-defined mathematically. I'm not going to show any equations more than this, but it's all laid out in the paper that's accompanying this presentation. So we went forward and used this model on an actual pilot that we did in Brampton, Ontario. I'm showing some pictures here. The top right is our surface water heat exchanger. It's just a coil of plastic pipe that was placed in an existing vault that was downstream of the pond. Bottom left there is a geothermal drilling rig that installed our borehole. Bottom middle is a mechanical enclosure. It houses pipes, gauges, manifolds, things of that nature to connect the ground heat exchanger to the surface water heat exchanger. And then bottom right there is a solar photovoltaic pedestal. We powered the whole thing with off-grid electricity. Don't need to discuss that much today because an actual installation would use a grid power that's available from the adjacent subdivision. So what we did is just a single borehole, small scale pilot that we wanted to test out our model and then try to size a full scale system. Some data from our pilot is shown here. So this is actual monitoring data. Top left there shows the cooling capacity in kilowatts as a function of the stormwater temperature. So the warmer the stormwater is, the more cooling we get, which is kind of nice. The different colors just represent different operational parameters of the system. We had different ground temperatures throughout the monitoring, and also we tested different hydronic flow rates. We wanted to adjust these parameters so that we could tune our model. Takeaway from that plot on the top left there is just that we are getting a substantial amount of cooling. So top right is the actual upstream and downstream temperatures from our surface water heat exchanger. So this illustrates the cooling effect that was happening on the actual stormwater. In blue is what's entering the vault, and in yellow is what's leaving it. You can see the gray dotted line is a flow peak, and the flow gets sufficiently high that both the blue and yellow upstream and downstream temperatures converge. This is just because it was a small scale pilot that didn't have the full cooling capacity to meet the full load of the pond. But as the flow rates start to get lower, you see that the blue and yellow begin to diverge. So we start to see the cooling happening between the upstream and downstream temperatures. And we see that the system works. In gray is what we predict with our model, and we also see very good agreement with the actual measured data in yellow. We used our model to size a full-scale system that's being shown here. At the top left, you can see that with no measures in place, the outflow temperatures from the pond are greater than 24 Celsius for 50% of the time. We can use 4 to 6 deep vertical boreholes, and that could keep temperatures below 24 Celsius for 95% of the time. Beyond that, it's quite difficult because there's these thermal load peaks that would need another technique to manage. Top right there, you see in blue is our actual monitoring data for the temperatures that are coming from the pond in 2019 throughout the season. And in yellow is a modeled geothermal system with 6 deep vertical boreholes. So again, you can see that we're getting much cooler temperatures from the pond with this system. In terms of benefits and drawbacks, we show that the system's effective, it works. We can describe it with relatively simple equations, which is nice, makes it highly engineerable. It's cost effective. The boreholes themselves are on the scale of $15,000 each. We think 4 to 6 would be required for a pond of this size. So the full scale system is maybe $100,000 to $200,000. There's no visual impacts on the pond, which is nice. And it's also space efficient because most of the work is happening underground. The drawback is, of course, is that it has a mechanical component in that circulator pump. That's a point of failure and could require periodic servicing. But I should just say that it's not the only thermal mitigation measure to use mechanical components. Controlled nighttime release would be another example. But overall, these circulator pumps, they're quite robust, inexpensive to replace. It can be winterized with the antifreeze solution that's non-toxic. And also remote monitoring can help as well to ensure that the system continues to function. Opportunities for improvements. So we used a plastic heat exchanger because it was quite easy to do. We think a steel parallel plate heat exchanger would be much more compact. You wouldn't need an existing vault. It would be a much smaller enclosure. It's also possible to implement the plastic pipe in different ways. It could be laid along the outflow pipe itself, or it could be buried in the trench, the aggregate of a cooling trench. So it could be used as a retrofit solution for existing systems as well. There's many different options. I just want to note at the end that we do have a web-based sizing tool as well that's going to help size these systems, and you can stay tuned to our webpage for that, or email me directly. So that's my talk today. This is my contact information if you're interested in reaching out. In general, we think this is a really promising new approach, and we plan on doing more work in this area to further refine this concept and have some more data that's available. And lastly, I just want to acknowledge the funding support that's provided by the City of Brampton for this project. Thank you.